Okay, time to start a new unit. Probably glad after all that tough trig stuff. So, decide to do the next unit as sequence and series. Normally, we would have done this unit a little later in the year, but uh, hopefully, we'll be going back to school sometime in the future. This unit seemed a little easier to teach by video than some of the other ones we had to do. So, I'm figuring if we are able to go back to class, it'd be easier to wait to do those other units. Obviously, if we can't, we can't. But so I decided to do the sequence and series unit. So we'll talk about what a sequence is in this video, and then the next unit goal will be about what a series is. And these you've seen before. You do them in algebra and I believe algebra 2. But time to do them again to refresh your memory and advance them a little bit more. So this unit, the reason I have the number on is because I changed the order. So this is about sequence and series. And goal 1, which you can read, is we want to be able to evaluate a sequence explicitly or recursively. So there's two different ways they can give a formula for a sequence. Now, I'll tell you what a sequence is in a moment, but basically some of them have patterns and some of them don't. The ones that have patterns can be written as a formula, and there's two main ways to express the formula. One's called explicit and one's called recursive. The explicit, I think you'll find to be easier. It's not really, that one's pretty simple to do. Recursive, the notation's a little weird, so I'm going to hopefully be able to get you to understand how the notation works so you know how to evaluate these things. The recursive isn't difficult either once you understand what's happening, but the notation's a little tricky to read. All right, so let's look at what a sequence is for this unit, or unit goal. All right, so a sequence, a really simple definition of it is that it's an infinite ordered list of numbers. So basically, you start with the first number, it can be whatever you want, and then the second number can be whatever you want, and the third number can be whatever you want, and you just keep listing them on and on and on until you feel like you're tired or you just can keep going. So the list can be as long as you want. A true sequence will just keep going and going. So here's an example of a sequence. The first number's 2, the second number's 4, the next number's 6. This is a nice pattern sequence. This is the sequence of even numbers, positive even numbers, I should say, because 0 and -2, well, those are also even. So this is the sequence of positive even numbers, and this goes on forever. I could keep making more even numbers. There's no stop to them. So after 14 comes 16 and 18 and 20, and eventually you'll hit 1,000,000 and 1,000,002 and so on. All right, so notice that this is an infinite ordered list of numbers. Now the order comes in the fact that these numbers can't just be however they want. I've arranged them so this is the first one, this is the second one, this is the third one. The notation they use to symbolize this is, they usually use a letter. We'll use A. That's the one they use most of the time. So they'll use A sub 1, A sub 2, A sub 3, and so on. Basically, this gives each member a list order. It gives it another number assigned to it. So what gets a little confusing later, and if you can get this concept now would be good, is that there's the value it has and what its list number is. So the first member is 2. 2 is its value, but its list number is 1. 4 is the next one. Its list number is 2. 6 has list number 3. Now I can jump ahead and go, well, what's the 7th member? It's list number 7, but its actual value is 14. Now sometimes there's a nice pattern. Notice each time you get a list number, you just got to double it to get the actual value. So sometimes there's a relationship between these, and we like that when there's a pattern between them, because it would be easy to know, like, what's the 100th member of this list. If I wanted A sub 100, following this pattern, A sub 100 should be the number 200. So sometimes there's a nice pattern to them, like this list of even numbers. Sometimes there's different kinds of patterns. So here's another sequence. This is another infinite list. This one's also predictable so long as the pattern keeps up. This one goes 3 is the first member, 6 is the second member, 12 is the third member, and so on. Now, if I wanted to know what the 8th member was, it helps if there is a pattern. Now, there's not always a pattern. people can make any sequence they want. Like I said, you could just make this break the pattern if you want. That's why usually they give you a formula to let you know, hey, this is what the pattern is. Now, if this pattern continues, notice unlike this one where they kept hopping up by twos, this one they're not going up by the same amount. It goes up by 3, then it looks like it's going up by 6, and it goes up by 12. So this one's not going up by an even amount. This one is being multiplied. Notice that each one's double the other one. If you take 3 and double it, you get 6. Double 6, you get 12. Double 12, you get 24. So the most likely next member of this, if this pattern continued, would be we'd want to double 192. And that would be the next member. I think that's 384. But so you could double that number and keep going. Now, some sequences have they have a pattern. You can come up with the next one, but it's not so easy to calculate what the next one is. This next sequence, you might recognize if you're good with your math numbers. This is the sequence of prime numbers. Prime numbers are numbers that only divide by themselves in 1. So 5 is prime because 5 divides 5 and 1 divides 5 evenly. Nothing else does. 6 isn't on the list because 6 isn't prime. 6 divides by 6, 1, 2, and 3. So prime numbers only divide by themselves and the number 1 because everything divides by 1 evenly. So this has a pattern as far as I could predict the next number. I need the next number that doesn't divide by anything but 1 in itself. 19 would be the next number. Then after that would be the number 23. The problem with this is that there is no way to predict the next one as far as some mathematical pattern. At least no one's ever discovered one. If you could actually discover a formula that generates these, you'd be super rich because no one's actually ever done it. Now, you can try to figure out what the next one is by testing to see if it's divisible. Like, for example, I know the next number is not even because it would divide by 2 and 2 is already on the list. But here's an example of it does have set numbers. We can find the other ones, but there's not an easy pattern to predict the next one. Like I said, if you do find a pattern to predict the next one, you share it with me, and then I'll turn it into somebody, and we'll split the money. Yeah, you probably don't want to split the money with me. You probably just want it for yourself. But if you figure out some pattern no one ever has, some mathematical formula that will generate them. So those are the prime numbers. And unfortunately, some sequences, you can make any sequence you want. They don't have to have some kind of pattern, or the pattern may be very difficult to pick up on. So this last sequence, I'm just showing crazy numbers that I just randomly, picked out of my head. So here the first member is 4.2. The second member is then -3. The third member is 14. Then it's 12.6. Then it's a big number. Then it's weird numbers. Then pi. Pi is a number, right? Pi is the sixth member. The seventh member is cube root of 2. Now this one doesn't necessarily have any kind of pattern you can pick up on. So what's the next one? Who knows? Someone would have to give us either a way to find it or tell us what it is. So notice that some sequences have a nice pattern to them. Some don't. Some have a way of, you could come up with a predictable formula, like these two have a nice predictable formula. We're going to study ones like this because these have nice patterns. Some of the other ones, like I said, this has a pattern, but no one really knows how to make a formula to predict the next one. You just kind of got to go through the work to see what the next one is. And then this one, just made up. All right. The key thing to remember is for each one of these sequences, so I can get them all, trying to get them all on here at the same time. Well, doesn't want to cooperate. The key thing about the sequence is, remember, there's the value and its list number. It's important that you separate those. That you know, for example, 17 is the 7th prime number. 13 is the 6th prime number. So this is the value of a sub 6. The 6 gives you that it's order number. You know, what order is it in? It's the 6th one of the list. Because in the formulas, they reference both this list number and the actual value. In fact, the first type that we'll talk about tries to use the list number to predict what the value is. And for some, like this one you can do it, this one you can do it, these two you can't do it. But then the second one actually references other list numbers. So, well, might as well just tell you about them instead of talking about them on this example. So let's go with the first one. The first one's called an explicit formula. An explicit formula basically gives you how to determine each value from its list number. So they'll give you something that looks like this. I'll put a sub n. Remember, n is the counter. So if you want, for example, the first list number, that n becomes 1, and then it just says you can plug in the list number to get what the actual value is. So if I want the first one, I plug in 1s. If I want the second one, I plug in 2s. What's nice about this formula is I can predict any one that I want. If I wanted to fast forward and go, hey, what's the 200th value? I don't need all the other ones. I could just put 200 and go, what's the 200th member? It would give me what the 200th member is. So let me show you this being calculated. Actually, there's this one, and then I have another example. You know what? I'll wait. I'll just show you the calculation. So I have another example on the right side. That'll be the next example. So just look at the left side for now. On the left side, it shows me calculating the first 5 terms of the sequence. So if I want what the first member is, because that's what the direction said, find the first 5 terms. So the first term I would plug in 1. So notice for the n's, if I want the n to be 1, the first list member, I just put the 1s into the formula. Calculate what it is, and the first member of the sequence is 2/3. Plug in the 2 for the n's, calculate what it is, comes out as 3/4. Plug in the 3's, comes in at 4/5. And then you might start to see a pattern. Plug in the 4's, it's 5/6. Plug in the 5's, it's 6/7. Sometimes you get nice patterns. You might be able to predict the next one without even calculating it. So looks like it goes 2/3, 3/4, 4/5, 5/6, 6/7. The next one's probably 7/8, and the next one's probably 8/9, and so on. So if you happen to see a nice pattern, sometimes you can then skip having to do some of these calculations. But overall, this formula will give us any member we want. Say I want the 100th member of the sequence. I'm only up to member 5. There's 6, 7, 8, 9, on and on and on. If I wanted the 100th member, I wouldn't have to calculate the ones in between. I could just go to this formula and go, well, if I want the 100th member, I would get 101 over 102. All right? That second example that I have up there, which you could have already seen, but basically, this is just a second example. Sometimes there's other operations in it, like that one's pretty easy because it just had a fraction with addition. This one also has a fraction. Not all of them have fractions in them, but this one has a fraction, but it has powers in it. So it wants you to, if you want the nth value, you need to take -1 to the n, and also take 2 to the n, and just keep plugging them in, 1, 2, 3, 4. So if we want the first 5 terms of this, that's what I had in the background here. So now focusing on the right side, same pattern. If I plug in 1, I get -1 to the 1, 2 to the 1. So the n is the powers, and I have to calculate what those are. So I get -1/2. For the second one, -1 squared is +1, and then 2 squared is 4. So I get +1/4. The third one comes out -1/8, and then the fourth one comes out +1/16, and then the next one comes out as -1/32. So once again, you could, if you want to find the 100th member of this, you could do -100 or -1 to the 100, which would come out as +1, and 2 to the 100 would be a huge number, but you could find it. Also, once again, there's a pattern of these. This is actually called an alternating sequence, because notice it switches back and forth, positive to negative, positive to negative. That's what that -1 power is doing. So term 1 is negative, term 2 is positive, term 3 is negative, term 4 is positive. So notice in this case, all of the odd numbered terms are negative, and all of the even numbered terms are positive. So if I want to know what a sub 6 was without having to do the formula, well, I know it's going to be positive due to the pattern. And the bottom, the pattern on the bottoms, they just keep doubling. So 2, 4, 8, 16, 32. The next one would be 64. So even without plugging in, I could know the next one is +1/64, and then the next one is -1 over 128, and so on. So basically, this is how you do an explicit formula. Hopefully, these are enough examples. You'll see in the homework there's a couple problems. You're just plugging in whatever list number you want, just plug it in for the n and calculate what it is, and it generates the sequence. Sometimes you can come up with your own formula for them. So if I go back, this is what I was mentioning, that some of these could have an explicit formula, like these. If I just do a sub n equals 2n, it would give me all the even numbers. This one would be a little harder because I'd have to basically do 3 times 2 to the n would give me these numbers. So notice if I do 3 times 2 to the power of 2, well, maybe I'd have to subtract 1. Maybe I shouldn't bother with it. But I'd have to keep doubling these. So I think it would be 3 times 2 to the n minus 1. But you can come up with formulas for them. We're not really going to be focused too much on coming up with the formula. We just, if they give us the formula, can we generate the sequences? And then just beware, like these examples, there is no explicit formula for them. This one I know there isn't one because I just made them up. This one, like I said, no one's ever found an explicit formula for it. And that's why I said if you could find an explicit formula for this, where you plug an n and get out one of these prime numbers, you'd be very wealthy, because many people have tried for thousands of years and no one's come up with one. So maybe there isn't one, or maybe we just need some new smart young person like yourself to come up with it. Let's talk about the second type. So this one's a little more difficult. This one's called recursive. So in a recursive formula, you get the value from other previous values. So I need to know like what the first value is, maybe to get the second. And then I need the second one to get the third. The problem with recursive is you can't fast forward on it. If I want the 100th value, I can't come up with the 100th value without maybe the one before it, or another term that's come before. So this was the one where you really need to understand the notation. So this says write the first 5 terms. Now, to explain how the recursive formula works is, notice that there's a sub n, but there's another a sub term in here. This is a sub n minus 1. So basically the way I'm going to get a term is I have to use another term. This means the term before it. It's the one that came before n, because it's 1 less than n. Now, this is the formula. This part is just a technicality. They just say that this formula is valid for numbers bigger than 1, integers bigger than 1. Why? Because they actually have to give you, in a recursive formula, they have to give you one of the terms. Because basically, if I just had this part, I don't have any of the terms, so I wouldn't know what to plug in. So in a recursive formula, they always give you at least one term. They have to tell you what one of them is, because basically, once you know one of the terms, you're going to feed it into the formula to find other terms. So they give me a sub 1, and then they want to know, well, what are the other 5 terms? So I know the first one. The way I'm going to find the next one is I want to find a sub 2. So to find a sub 2, I'm going to have to plug a 2 in here. And I'm going to get a sub 2 minus 1, which is a sub 1. So basically a sub 2 is based off of a sub 1, which I know, which I'm going to plug in. So I'll show that on the board behind here. So once again, I've got 2 examples up. We'll look at the one on the left first, and then I'll show you the one on the right. So how do you do the recursive formula? Well, the recursive formula needs previous values plugged into it. So I wanted to find the first 5 terms. A sub 1 was given to me, so I get a freebie. How do I get a sub 2? Well, I need to plug the 2 into the counter. I get a sub 2 minus 1, which is a sub 1. A sub 1, I know the value of. A sub 1 is 1. So I plug in that, and then I get 1 plus 3, which is 4. So what's the second term? The second term is 4. Then, how do I get a sub 3? Well, I need to take 3 minus 1 in the counter. That's the second term, and the second term was 4. So 4 plus 3 gives me 7. And now I keep going. Basically, what this notation means is the way I get a term is to take the term before it. So notice for a sub 4, I basically need the term before it, a sub 4 minus 1, or a sub 3. So I didn't write it this time. A sub 4, I need a sub 3. A sub 3 I know is 7. It becomes 10. And then you start to see a pattern. They keep going up by 3s. So you might know the next one's 13, the next one's 16, but just to be able to, get it from the formula, if I want a sub 5, I'll use a sub 4 plus 3. So basically a sub 5, I need the term before it. So notice in each case, the 1 plugged in to give me the 4 then plugged in to give me the 7 plugged in to give me the 10. So I keep using the previous term in there. That's what this notation means. So this is the counter. It's basically saying if you want the nth term, you need the n minus 1 term. So if you want a term, you need the one that was before it. So you're always taking the one before it, adding 3, and coming up with a new list. If you get to see a pattern, it becomes easier because at first it's a little difficult to evaluate them. But once you see the pattern, it's not hard to know the next one will be 16 because basically I'm going to take 13 and add 3 to it. All right. So the next example, once again, it was up there, so you already saw it, but just to show it officially. This second example does the same thing. It basically says if you want term n, you need to double term n minus 1. Remember, this is the counter, so if you want the nth term, you need to double the term before it. So if I wanted the 8th term, I need to double the 7th term, for example. Now, I don't know what the 7th term is, and I don't know what the 8th term is, but they have to give me one of the terms. So once again, they usually start you out with the first term. And this thing just says, here's your first term. This formula works for all the terms bigger than 1. So you don't have to really worry about this. This is just to define how this formula works. So you get the first one. After the first one, you use this formula. All right. So once again, you already saw the work behind, but I'll go through and explain it. This time I put little arrows in to show you how it keeps feeding into itself. So if you understand the way the notation works, once again, how am I going to get any term that I want? I need to double the term before it and add 1. So they gave me a freebie. They gave me the first term was 3. Now in the second formula, for the second one, they say double the first term, add 1. So I'm doubling that 3 and adding 1, getting 7. Then I'm doubling the second term, doubling that 7 and adding 1. And then I get 15. I'm going to double the 15 and add 1. Get 31, double the 31 and add 1, get 63. So if I had to keep going, I'd have to double 63 and then add 1 to it to get the next term. I think that'd be 127. All right. So the problem with the recursive formula, like I mentioned before, is say I want the 100th term. I can't just get the 100th term because say I want term 100. I will need to double term 99, and I don't know term 99. In order to get term 99, I would actually have to keep doing this until I got to 99. Now, if you happen to see a pattern, sometimes a recursive formula can turn into an explicit formula. You can go back and forth. Once again, that can be difficult sometimes to come up with a conversion formula, so we're not going to go that deep into it. But realize with the recursive formula, I can't just jump ahead and get the next term if I want to jump to like term 100. I'm not able to just fast forward through them. If I want to get to term 100 for these, I have to actually, according to this formula, I have to keep going. I have to get the 6th one, the 7th one, the 8th one, and when I finally get to the 99th one, I'll be able to use the formula to find the 100th one if that's what I wanted. All right, so recursive is a little more difficult. Hopefully you see this pattern, and that's why I put the arrows here to show you, look, the previous answers feeding in. All right. I'm going to do one more advanced example, but I'll do that in another video that will be below this one in the links. All right. This should be enough to do that homework assignment. Like I said, I wanted to show one more advanced one that sometimes appears, or they give you SATs or college entrance exams. You want to be able to handle something that's even a little more difficult than these. So, but this lesson's enough to at least do those homework assignments. All right. So get the next video going in a moment here. Till then.